Hi. So in the last lecture I talked about adding vectors graphically, where we took the tail of one vector and put it at the tip of another vector, and that's the way we added them together. Now, that's great and all, but it may not always give us actual numbers that we can work with for problems. So there's another method of adding vectors, and that's adding vectors by components. And that'll be the topic of this particular lecture. But before we do that, I need to remind you guys of what vector components are. So in this graph right here, I've got vector A, and we've drawn out legs of vector A in the x direction and the y direction. So literally, the x component of A is, well, as far as A goes in the x direction. And the y component of A is as well far as A goes in the y direction. And so those are our vector components of A. Now I can add a vector A and a vector B together. And you guys can see that we've done this graphically. We put the tail of B at the head of A, and then what did we do? We drew another vector from the beginning of A all the way to the end of B, and that's our vector C. So that literally C is equal to A plus B. Now that's great. I've done it graphically, but I can also do it with components. And how do I do that? Well, I break vector A up into its x and y component. And I also break vector B up into its x and y component. So I find those components of each one of those two vectors. And maybe I have to use some trig and whatnot to do that, but that's what I do. After that step, I take A sub x and B sub x and I add them together. And added together, that'll tell me how far vector C goes in the x direction. So literally that will give me C sub x there. And then I do the exact same thing with the y components. Oops. All right. So if I want to figure out the x components of vector C, well, then I add up the x components of A and B. Same thing with the y components. Okay. And in this way, it gives me actual numbers to work with. You know, if I want to know the magnitude of C, well, if I were doing it graphically, unless I get some really nice vectors that, you know, maybe point, you know, straight to the right and straight up, you know, I end up having to do a whole lot of geometry, maybe pull out some graphing paper, something like that. But adding vectors by components actually gives me a way to get to actual numbers and sizes that's maybe not quite as tedious as pulling out a graphing paper and a ruler. All right, so let's look at an example problem. In this example problem, we've got Tamika. Tamika drives 5 kilometers to the east. And then after that, she drives 10 kilometers in a direction that's 30 degrees north of east. So literally, it's like, you know, you look at the direction of east and then you go like 30 degrees above that, and that's the direction that Tamika's heading. So let's maybe draw this out here. Okay, so maybe 5 kilometers, call this vector A to the east, and then maybe 10 kilometers, call this vector B, at a 30-degree angle north of east. And then my vector C, or my vector R, or whatever it is I want to call my vector, is just A plus B added together. And it's that vector C that we want to find the magnitude and the direction of. So we want to find the size of C, and we also want to find that angle theta that I've drawn in right there. Well, in order to do that, we're going to take advantage of exactly what we saw on the previous slide, that C sub x is equal to A sub x plus B sub x, and that C sub y is equal to A sub y plus B sub y. All right. Of course, I need a little more space, so let me move on to maybe a blank page. All right. So if we think about vector A, it said that what happened, that she drove 5 kilometers due east. And I don't know why my stylus doesn't want to write it there. 5 kilometers. I probably have something on the tip of my stylus. She drives 5 kilometers due east. How far does she go in the y direction while she's driving due east? Well, 0. She doesn't go north at all when she's making that first leg of her trip. So there's the x and y components of that vector A. Now vector B, a little more difficult. Vector B, what? Was 10 kilometers. At a 30-degree angle. North of east. Okay, so there's B sub x and B sub y. So I can use trigonometry to figure out what B sub x and B sub y are. Let's see, if I think about cosine of 30 degrees, SOHCAHTOA, that's adjacent over hypotenuse. So adjacent over hypotenuse. That is B sub x over 10 kilometers. That's supposed to be a kilometer there. There we go. So then B sub x would be what? 10 kilometers times the cosine of 30 degrees, which ends up being 8.66 kilometers. And that's important, so I'm going to put a box around it. And if I wanted to figure out B sub y, well, it's the exact same process, except it's sine that I would use this time, because SOHCAHTOA, sine's opposite over hypotenuse. That would give me B sub y over 10 kilometers. So now my B sub y would be what? 10 kilometers times the sine of 30 degrees. And this ends up being 5 kilometers. All right, great. So now I've got my x and y components of both A and B. All right, so I can add them together. And I need to make sure that when I do this, I add them correctly. So that I'm adding the x component of A to the x component of B. Funny story, this is the second time I've recorded this video. The first time, I did it wrong because I misremembered what was what. And I've got notes over here to the right of me, but I just didn't look at them. So 8.66 kilometers, that gives me 13.66 kilometers. The struggle is real. Okay. 13, there we go. All right, well, what about C sub y? C sub y is A sub y plus B sub y. This looks like 0 kilometers plus 5 kilometers. That gives me a y component for vector C of 5 kilometers. All right, so now that I've got those components, what I can do is I can kind of draw out my vector triangle for vector C. So there's C sub x, right? Maybe right there is C sub y, so this is 13.66, and this is 5. And there's vector C right there, and there's some angle that I want. All right, so if I want to figure out vector C, the size of vector C, then I can just use the Pythagorean theorem. Here in a minute, I'm going to start drawing with my finger. Well, maybe not. All right, so if I do the math there, square 13.66 and square 5, and then take the root, I can figure out then that my vector C is 14.55 kilometers long, or 14.5 kilometers long. There we go. So there's my answer for the size of C. Now I still have to figure out the direction. And in order to figure out the direction, I can use tangent. I can actually use any one of the trig functions I want, but I'm going to stick with tangent. Tangent is opposite over adjacent. So Katoa. So this is 5 kilometers over 13.66 kilometers. So theta then is going to be the inverse tangent of 5 over 13.66. The kilometers cancel each other out. And that gives me an angle that is 20, oops. Woohoo. That gives me an angle that is 20.1 degrees. And my answer is not yet complete. I've got 20.1 degrees, but I didn't say from what. Well, it's 20.1 degrees in a direction that is north of east. And now I have my complete answer. There we go.